This past week or whatever, you guys had a bunch of problems due, and it seemed like there were some issues kind of finishing stuff for some of us. Does anybody want to ask some questions on pieces from the homeworks before we get talking about the review stuff? I saw lots of notes about asking class and things left blank, and so I figure I'm just going to start by opening the floor here since it's been a couple of, 10 days or whatever since I've seen you guys. Does that feel okay? Giselle?
Can you do number 60 on the problem set?
Yeah, of course. All right. So I would hope that you would have elected to start with the right-hand side. Is that a fair assumption? You wanted to start with the left-hand side? You could do that. That's okay. I mean, I can do it. You start with sine to the fifth x.
Yeah. You can break it down.
Okay. That's fine. You can do it that way. You absolutely can. I wouldn't have thought would be the place where you would start, but it's surely fine. It's probably the easier way to do it because then you're foiling rather than factoring. But like the factoring here is not difficult. Giselle, am I fair with my assumption that this is where you started?
Mm-hmm.
Okay. So this looks a bit like a quadratic to me, right? It's certainly in the quadratic form. Everybody's agree with that? Where you have three terms, you have a constant term, you have a middle degree, and then you have a biggest degree where the biggest degree is twice the middle degree. Everybody agree with that? So this will just factor the same way like that would. Actually, let's do, So you'd have something like that. So I'm just looking for two things that multiply to give me 1 and add to give me -2. Those would be, oh, come on now. Multiply to give us 1 and add to give us -2. -1 and -1, right? Yeah. So it'd be like 1 minus alpha times 1 minus alpha. So if I go back up here and apply that to what I have, where alpha is cosine squared, Giselle, so far so good?
Yeah.
What's 1 minus cosine squared equal to? That is sine squared. That's P1, which is a little bit of rearranging, or you could make a direct substitution for 1 with cosine squared plus sine squared and then do some canceling. Either is okay. And then sine squared times sine squared times sine is sine to the fifth. And we're done. Does that feel okay? I know it's disappointing when you see Mr. Kulik do it and it takes like 3 steps and you're like,
it's just hard to see what to do from the get-go. So I see it after you do it, then when I'm actually doing it, it's I don't know.
Yeah. I have some good news about that though. Coming up. We'll get to it. Elena.
Okay, I have 2.
Sure.
First one is 38 for the problem set.
Okay. 1 second. I don't think I have that number dropped in yet. So let me grab that. Copy. Oops. $38. Okay. Oops. So I notice that I have two different kinds of trig functions here, sine squared and cosine squared, right? So this is the trick. I'm going to divide both sides by cosine squared x over 3. And I'll show you why in just a second. Now, typically, is this a good idea? If I divide both sides of an equation by something with a variable in it? Typically not, right? Why not? Could be getting into a situation where you're dividing by 0. But I know I'm not having to worry about that because sine squared over cosine squared is just tangent squared. So like, if I'm dividing by 0, I'll catch that when I deal with the tangent piece because I know when tangent is undefined. So it's okay in this kind of situation. Elaine, are you happy with that? Okay. So now I'll square root both sides. So x over 3 is equal to the tan inverse of plus or minus root 3. So when I go to my unit circle, I'm going to look for every place where, again, tangent is y over x, right? And I know that there's no place where I have like root 3 and then 1 as coordinates. But I do have a place where I have like root 3 over 2 and 1/2 as coordinates. And those will reduce down to give us square root 3 over 2 also. So I'll just go and check my unit circle real quick. Somewhere on here. There it is. So where the y has to be square root 3 over 2 and the x has to be 1/2. So I have pi over 3 and then 2 pi over 3 and then 4 pi over 3 and then again at 5 pi over 3. So I have 1 pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. But those aren't my answers to anything right now. I'm going to do my infinite solution first. And the reason I'm going to do my infinite solution first is because my x has a coefficient on it. So when I solve for x, I need to multiply both sides by 3. So when I do that, I get pi plus 6 pi k. And then 2 pi plus 6 pi k. And then I get 4 pi plus 6 pi k. And then I get 5 pi plus 6 pi k. So that's my infinite solution. I think that's, what is that, part B? Is that right? Okay. Now part A, we want things from 0 to 2 pi, correct? I forget. Was it, one of these was a parenthesis, right? Is it this one?
Yeah.
Okay. So when I do that, the only solution I get is the first one, right? If k equals 0, the only thing that's between 0 and 2 pi is the first solution from those infinite. All the other ones are too big. And if I make k be negative, then they're all way too small because they're all negative. Everybody's cool with that?
Just for like whatever, like for part B, Did you say that you could only write one of them, and then, or do you have to write all four of them?
No, you don't have to write all four of
Okay.
them. Here you could combine some of these. Yes, for sure.
Got it.
But most of us aren't going to bother doing that, right? It's usually clearer what the answer is if I just write it this way.
Right.
But certainly, yes, for compactness sake, you could combine some of these together. Probably. I'd have to look. Maybe you can't. What's the interval for C then? That's like negative 2 pi to 4 pi, is that right? Oh, okay.
Or no, C is 2 pi to negative 2 pi to 2 pi.
Okay. Are they bracketed both?
Yeah.
All right. So if k is 0, I get pi and 2 pi from those first two solutions, but the rest of these are garboed, right? Those are too big. If k is negative 1, that's negative 5 pi too small, negative 4 pi too small, negative 2 pi, that's okay. And then negative 1 pi, that's okay. And then D is, what is that, negative pi to 4 pi or something? Is that what it was?
Yeah.
Is those both bracketed also, or is there a parenthesis on one of those?
There's parentheses on the 4 pi.
Okay. Thank you. All right. So I'm just going to use my answers from before. So negative pi will fit in that interval. Pi will fit in that interval. 2 pi will fit in that interval. Negative 2 pi is too small. And then I have to see if k is 0, I get 4 pi from the third solution, but 4 pi shouldn't be included in my interval. 4 pi is actually too big, as well as 5 pi. So it should just be those three answers there. So if you're able to get through the tangent piece, the tricky part is doing the infinite solution first and making sure that when you multiply by 3, you multiply the coterminal piece by 3 also. Because if you're not adding 6k here, everything gets all mucked up. But if you can get that far, it's usually pretty easy to get whatever interval I give you if you have the infinite solution. Just a matter of like checking your k's until you find something, until it's too big or too small. You know what I mean? Are you happy with that, Elena?
Yeah, it was the, like, getting it down.
Getting it to a tangent that was,
Yeah.
I saw a lot of people skip those ones where it was, the trick was to get it to a tangent. That happens on several of those. 29, that's the trick. 26, that's the trick. 37, that's the same trick. You know, there's probably a 38 that we just did. That's the trick. There's probably another one that I'm just not noticing right quick while I'm looking at it. But any of those where you have sine and cosine together, that's probably what's going to happen, is you're going to end up dividing and getting a tangent out of it. Giselle.
Can you just do the setup part, like for 37, like to get it down to like just like?
Yeah, I would just subtract the sine of pi over 2 to both sides and then divide both sides by negative cosine of x over 2. So you have tangent equal to negative 1, or equal to 1, or tangent of x over 2 equals to 1. Excuse me.
So after I subtract sine, the sine x over 2, then what do I do after that?
Divide by negative cosine of x over 2. And that'll give you then 1 equals tangent of x over 2.
Okay.
And then from there, it's the same kind of setup as we just did. Except it's easier because it's not a plus or minus. So there's less sets of infinite solutions, which is nice, right? We'd rather have fewer of those guys. You know what I'm saying? Is that all you needed?
Yeah.
Okay. Sure, sure. Who's next? Happy to do some more. Okay. Oh, Elena.
Can you do 62?
Certainly. So that we have already. Which side did you start with?
I tried to start with the left side, but it didn't get very far.
Okay. We can do the left side. That's fine. It's probably 6 of one, half dozen of the other. So what I'm noticing right away when I look at this is I'm looking at these denominators. I know that sine squared is 1 minus cosine squared, which I can factor like a difference of two squares. One of those factors is 1 minus cosine, so I'm pretty sure that this is basically going to be a factoring problem. So I'm going to start by trying to factor this. I'll make sine squared equal 1 minus cosine squared right away, but the bulk of this is probably going to be the factoring piece. So to factor this, I'm basically going to think about this as a quadratic. I'm going to just say alpha is equal to cosine. So I'm just going to be trying to factor something like this, right? Now, this is a little bit tricky because the leading coefficient is not 1. So we have to be a little bit more careful here. The two things have to multiply to give me the constant term times the leading coefficient, and then have to add to give me that null term. So what multiplies to give me -4 and adds to give me -3? -4 and +1, right, people? Should be really fast with these. So I go ahead and I rewrite my quadratic where I've replaced the middle term, -3 alpha, with -4 alpha plus 1 alpha. I'll make my two groups. From the first group, the greatest common factor is a 1. Well, that's disappointing. From the second group, the greatest common factor is an alpha. And then if I look at each of these as a term, the greatest common factor between those is 1 minus 4 alpha. When I factor that out, what's left is 1 plus alpha. So if I go back here, remembering that alpha is cosine x, I have that. And then if I just factor my denominator as a difference of two squares, I get exactly what I needed after I reduce. And I'm done. Now again, a little bit tricky because you had to remember this a little bit more complicated factoring pattern from your previous algebra course. But if there's one thing that you should remember from your Algebra 2 course, it's factoring and solving quadratics. That is probably the thing you spent the most time dealing with, was solving polynomials and factoring quadratics and factoring polynomials and solving quadratics, because it becomes a subroutine in so many of the other function types you dealt with in the second semester of the course, that we should really be pretty good at that still. I know it's been a while though. But that was the trick with it, Elena. Had you started with the other side, which you certainly could have done, the trick there would have been to recognize again that that looks like half of a difference of two squares. And you could do this to start with. And it'll probably be a little bit quicker because you can avoid having to do that difficult factoring. It's just one of those, like, do you see it or not? Yeah. Like the obvious thing would be to start with the left-hand side. Although in this case, the easier thing from a calculation standpoint would actually be the right-hand side. But seeing to do this as your first step is not super obvious. But if you see it, boy, that's a time saver. That paper go. Okay. I wanted to talk about a couple of things from the homework quiz that you guys did on Friday last time. Overall, I know. It's okay. I have a different version for you. It'll be fine. The quality of these were such that I need to talk about it. Don't be embarrassed. It's fine. Do you know how to do? Are you all experts at mathematics? No, it's okay. This is part of like this is
I'm right on the verge.
This is part of like the feedback process, right? Like when I see that like the whole class struggled on something, that's not your problem, that's a me problem. So I'm just going to try to go back and like walk through some of these things a little bit slowly, talk about some of the common mistakes that I saw, try to get us some more feedback. When everything, when most people are getting like 9s and 10s, it's less of an issue for me. When like almost nobody gets any of the simplifying ones right, it's a me problem. It's something I did. I didn't do a good enough job.
Are those in?
I think I just put them in like a few minutes ago. Just stop. Don't look at it right now. It doesn't matter. Look at what I'm doing. All right. This was the first one. Right? Does this look familiar? Unfortunately. Okay. First thing we do is we look for algebraic things, right? You want to start looking for algebraic things to do before trigonometry, before identities. Here you have two things being multiplied together, or two pairs of things that are being multiplied, right? Are there any like terms? No, right? X is not a term, guys. It'd be like saying square root of x times log x. Oh, x is a like term. It's like, no, they're not. No. It's stuck inside of that trig function, right? So there's no simplifying that I can do multiplying these pairs of things together. Is there and they're not like, I certainly can't subtract them. Is there anything in common? Could I do any factoring here? No, there's not, right? One is sine squared and secant squared. The other is cosecant squared. The other is tangent squared. There's nothing in common between those. So what am I going to do? There's no algebra to do. Look for an identity. Does anybody see anything obvious to do? Yeah, probably rewrite everything in terms of sine and cosine, because there doesn't seem to be like one glaringly obvious thing to do here, right? Right? When in doubt, if you're not sure what to do, writing everything in terms of sine and cosine is probably a good idea. Let me put it this way. It's usually not I will say it's almost never an unhelpful thing to do. Maybe not the best thing to do, but it's usually never unhelpful. It's usually walking us closer to our answer. Everybody's okay with what I did there? Okay. What do we see? Can I cancel these guys? That's okay. Can I cancel those guys? No. Why not? They're both on the bottom and they're both subtraction, right? Could I have canceled these guys? No! Why not? Are they being multiplied together? No! Can you cancel things that are not being multiplied together like that? No! Look at your symbols, guys. Look at your symbols. I saw lots of people doing stuff like that. That's okay. I'm just giving you feedback. The me screaming was supposed to be funny, not berating. I'm just trying to have a little bit of fun. Good, I scared you a little bit? Maybe? Okay. All right. So what do we have now? Sine squared over cosine squared minus 1 over cosine. Don't forget the 1. Lots of people would like reduce something from the numerator and just write as cosine there, not 1 over cosine. That's a problem. As an aside, I saw lots and lots and lots of people not writing their variables. I'll mark you down for that on the test. If you go and write if you write this with no x's, I'm marking that down. I will take points off for this. Please be cautious about making sure you're writing your variables. I'm giving you a warning now. I'll try to remember to warn you again on the test day. Okay, what do you want to do next? So yeah, a couple of different people had a couple of different suggestions. So I heard Ava say these have a common denominator, so we can write it this way. That's okay. And I heard Giselle, I think, say that we can turn these back into like tan squared and secant squared. Either of these is fine. That's okay. Both of these are going to get you the same spot. They're both correct. Either is good. Ava, what did you do next? It's close. 1 minus sine squared is equal to cosine. So what you'd have to do is factor a negative 1 out first. And then you have that, which is going to get you the negative 1. But yes, right idea, 100%. A little poor on the execution because you couldn't remember the identity without looking at the sheet, but that's okay.
Like that.
Yeah, it was something like that, which is good enough, right? All right, Giselle, what did you want to do from here?
I got no clue. I just thought it.
Okay, that's okay. We have things squared that are being added or subtracted. What set of identities would we want to go look at? Pythagorean. Let's go look at the Pythagoreans and see if there's one that relates tangent and secant. Yeah, P3, secant squared is tangent squared plus 1. Well, let's do that. Secant squared is equal to tangent squared plus 1. Now, critical there that you put the parenthesis around that, because secant squared is negative. So anything you're turning secant squared into, all of that stuff, the negative sign applies to. Right? That was an identity. Secant squared is tangent squared plus 1. And then we can just distribute the negative. And those two like terms combine to give you 0. And you're left with negative 1. Either way of going about that would have been fine. Right? So good instincts from both of you guys. Right on. Just about like finishing them out. And on the test, on a simplifying problem like that, it's going to all go down to like a single term, right? It'll just go down to like negative 1 or 7 or sine x or, something like that, where it's going to be like down to a single trig function or a constant. Okay, it's not going to be something kooky. Giselle?
So anytime it's like sine 2x minus 1. Like
Sine squared
or-
x minus
yeah,
1.
sine squared. So if like the minus 1's on the right side, always factor in -1. Just change it.
Sure, yeah. Yeah, that's all we're doing. If the signs are flipped, if the signs aren't right, if it's like, oh, that should be minus positive and I have positive minus,
Yeah.
then just take a negative out and it flips the signs and you just have an extra -1 floating around. But that's okay. You can do that. So again, like if you count, what was that? 1, 2, 3, 4, 5 steps or something? That's kind of about as long as I would expect to deal with. The other one, that I don't think, if I recall, some of you guys got this right. There are a couple of us, handful of us that got this one right. I think honestly more people got this one right than the previous one, which was surprising to me. But that's okay. Nobody went and did this the quickest way, which wasn't surprising to me. So if you take a look at this, again, we're starting one of these. What's the first thing we want to look for? Algebraic. Now, we have like 4 things that are being added or subtracted here, right? Obviously, none of them are like terms. And each of those 4 things that are added or subtracted are being multiplied. And none of those pairs are like terms, right? So there's no like combining like terms thing I can do just with my operations. But there's still other things I can check for algebraically. There's factoring that I could try. Now, if I look, there's no greatest common factor amongst all 4 of these things. But I do notice that, like, this pair of things has a sine squared in common. This pair of things has a cosine squared in common. Since they're just things that are being added and subtracted together, I can move stuff around as long as I keep the subtraction symbols in front of the same stuff. Right? So I'm just going to start by rewriting that way. And then I'm going to do like a factor by grouping kind of thing. So from the first group, my greatest common factor would be sine squared. From the second, the greatest common factor would be cosine squared. Let's take a look at these guys. What do those scream to you? Pythagorean. Yeah. So let's go look at the first one. Is there one that relates tangent squared to secant squared? Yeah, that was P3, right? That secant squared is tangent squared plus 1. And remember, since the secant is negative, I got to make sure that that negative sign is going to be applied to the entire thing I'm replacing it with. And if I go look here for something that relates cotangent squared to cosecant squared, that would be P2. Cosecant squared is 1 plus cotangent squared. And the same idea, since the cosecant squared is negative, I need to make sure that applies to the entire identity. Just distribute our negatives through. Howdy, brother.
You want the back of each of these blank, right?
The back of each of these blank.
Yeah. You don't want them back to back.
Yeah. I gave you one-sided copies. Oh, I just put it in the wrong spot.
Oh, okay.
They're one. I'm sorry.
Yeah, okay, good. Okay, good.
Okay. Right, so we have this. Everybody's okay? Combine some like terms. What do we have? -1 times sine squared plus -1 times cosine squared. Factor negative sign off. What does that look like? That's P1, right? I think a couple of us did this right, taking everything in terms of sines and cosines, and like, it was a lot of steps. But that wasn't so bad if you factored at the start. Again, the point of this was to remind you, like, look for algebra stuff. Look for the algebra stuff. The instinct is like jumping straight to the identities. But I would say that in some of these problems, like, especially the verifying ones that will be, that you guys have done in the homework and stuff, I would say at 2/3 to maybe 3/4 of the steps are just algebra things. Right? So like, don't discount that stuff. Really got to look for the algebra stuff. It can make life a lot easier than trying to grind through everything in terms of sine and cosine. And like, if you don't go that route, you're like, you have to make common denominators and there's a bunch of factoring that has to happen. And like, it gets pretty messy. It's doable. Like, you guys are all capable of like grinding your way through something like that. But it's just like, there's usually a better way of doing stuff. Like Mr. Kulik typically doesn't want to give you something that's like, oh yeah, it was a 12-step to get to the answer kind of problem. I'd prefer to give you something that's 5 or 6 steps. And this even, I think, is more than I would give you on a test. Because this was tough. For sure. If you didn't catch the factoring trick at the beginning, it was a lot. And I purposely kind of obfuscated the factoring by like not putting the pairs of things that you'd use the greatest common factoring on next to each other. So you really had to think like, can I just rearrange this to do the greatest common factoring even if you saw it? Okay. Let's talk about this, the test format here. So the test format's as following. There's going to be 11 questions. You only have to complete 8 of them. Ooh. So there's 3 required questions that you have to do all 3 of these, and then you have some choices. Those 3 required questions are going to be of the following types: using trig find some trig functions using a reference triangle. So like those would be similar to, like these problems 1 through 6. Where was I? Use identities to find the value of something. Again, that's just like the other way of doing problems 1 through 6, right? Solve trig identities for specific angles on the unit circle. That's 15 to 46. That's just the solving problems that we've been doing. And then simplify trig expression, that was like, 7 through 14, worksheet 2. Those 2 things we just did, that's all just simplifying. So you're going to get 3 out of those 4 as required. Okay. The other 8 questions are going to be identity proofs. You can do any 5 you want. So in the case like Elena says, sometimes I look at it, I'm just not sure what to do. Well, you can skip 3 of those if you're just like, I don't have a clue what to do with this. Great. I'm sympathetic to that. I know that these are not easy to like look at and instantly know what to do. So I'm going to give you some freedom there where you can choose to do the ones that like, oh, okay, this looks like a nightmare. I'm not going to worry about it. Oh, I know what to do with this. Let me do this one. So you have some freedom there to avoid the things that you don't feel very comfortable with, which I think is probably a nice compromise. Where it's like, the proofs, when I list them, are not any kind of order of difficulty, so they don't get more difficult as the test goes on. They're just kind of randomly placed in there. I wrote these things so that they really require only 2 to 4 steps in like the most efficient path. Now, that does mean if you do more than 4 steps, you're doing it wrong. No, it just means that maybe you're taking a more circuitous route than necessary, but that doesn't mean it's going to be wrong. All the questions are like the same amount of points as the proofs go. They're all just like 5-point questions. So like pick the 5 easiest ones. I'm going to grade the first 5 that I see, even if it's blank. So if you're skipping one, you need to cross it out, obviously, like write a big X or a giant skip underneath the problem. So I'm not confused as to like what you're deciding to skip. Even you can write work there and then just put a big giant X through everything if you're like, yeah, I'm skipping that one. That's okay. You don't need to erase it all, but you do need to like make it super clear that do not grade this one. Now that doesn't mean like a little tiny X right there. Like we're talking about, like don't be shy. Use your pencil lead. Make it super obvious. Like giant X's is what I prefer. Okay. Any extra questions you solve are not graded. I'm not going to grade like, oh, I'm going to take your best 5 out of the 8. Nope. I'm just going to grade your first 5 and then I'm stopping. Okay. So there you go. And then on the identity or on the review here, I have these broken up. What do I have? I have like 5 teams, right? Do you guys want to do these collectively or do you want to just work on them on your own? So let me say this is how I would do this. If you wanted to work on them collectively, we'll break into 5 groups. Each group gets 3 of these. We'll do them in the collaboration space so everybody can look at what you did. If you want to do them on your own, then I'll just get out of your way and let you work on them on your own. Which would you prefer? On your own. That's fine with me. If you get stuck on something, you want to talk about something or walk through something with me, that's perfectly fine. If you want to work with your neighbor through something, definitely fine. I often think that these identity problems are quite helpful, like talking it through with somebody. I think that can be really productive. So if that feels like a good idea to you, feel free to be doing that. As a reminder, the problem set for this weekend is going to be the review pack and worksheet 1. So if you haven't done either of those yet, those will be the assignment for this weekend. Giselle?
For the third bullet point on like the for your required questions, which questions were those in the problem set?
Like 15 through 46, the solving problems.
Oh, okay.
Talika? Certainly. Jacob? Certainly.
All right.
Okay.
Sorry.